All right, looks like we're going. Okay, so we only have 2 chapters. Actually, it's kind of weird because Bougie's testing over pretty much the same stuff, but hers is 4 chapters because each of hers goes into more depth. But I just picked out what we needed. So these pictures and stuff I'm showing you is actually from 4 different chapters. Okay, this is just reviewing everything. Bring it back to mind. We started out with fluids. Oh, I have to record each slide. Okay. Thanks for letting me know. Okay, so I'll have to repeat all that later. Okay. Okay, what is pressure? Pressure is force over area. Pressure in liquids, hydrostatic pressure. This is when the liquid is just staying in place. Later on in the chapter, we get into moving fluids. Pressure increases with depth. Pressure in gases is primarily thermal. Okay, we didn't talk too much about that. Pressure is constant in a container. Let's see what happens. All right, talked about buoyancy, Archimedes' principle. Buoyancy is the upward force a fluid exerts on an object. You will have a problem on the test with buoyancy. Archimedes' principle says that the buoyant force equals the weight of the fluid displaced. So if we have something just floating, like you see in this picture, and it's stable, it's in equilibrium, whatever our weight is down, that is equal to our buoyant force going up. And we can figure out how much our buoyant force is by looking at how much of this is underneath the water, take that volume, and figure out how much that water would weigh. So the buoyant force going up is going to be equal to this right here, which is also going to be equal to the weight of this whole thing since it is floating. So if you know the force up, the force down, you can do things like come up with the density of the block and things like that. This one gave some people problems on the test. Not on the test, on the homework. Okay. There is a problem similar to this on the test. So you want to make sure we understand this with Bernoulli's equation. We have an ideal fluid. It's incompressible. So when we have this fluid flowing through this, and it shows that we are flowing from this side to this side, which means we must have low pressure up here because fluids go from high pressure to low pressure. What would be the reason that it's low pressure up here? Because it's up higher, which would make you think, well, I guess this is lower, so the deeper you go, the bigger the pressure. So that's one thing, but what else is changing the pressure up here?
The diameter of the pipe that's going through.
All right, we have a smaller area, which means however much fluid comes in, we have that much fluid going out. Well, we have a smaller area for it to go out, so it's going to have to be going out a lot faster. And the higher the velocity it is going out, the less pressure it's putting on this area around there. So we have lower pressure because we're up higher. We also have lower pressure because it's going faster. Okay, on your homework, we had the continuity equation, which was Q equals area times velocity, and we used that to figure out this velocity. So on the test, you'll have something similar to that. You might have to figure out this velocity first, then plug it into Bernoulli's equation, which is P1 minus P2 equals, and it has all of those equations afterwards. So I would be sure to have Bernoulli's equation down. All right, so this one, hydrostatic pressure at a depth. So this means as you go, like in a swimming pool, you go down further and further and further. The deeper you are, the more pressure there is. You can feel it on your ears. This right here would be like the gauge pressure. The pressure from just the fluid would be the density of the fluid times the gravity times how deep you are. And then you have to add onto that any pressure that's on top of that fluid, which is usually atmospheric pressure. So this is pretty much your total pressure equation right here.
The atmospheric pressure again is like 1 point something times.
101.3 pascals are, right, 101.3 pascals are 1.013 times 10 to the 5th kilopascals. All right. And I would write that down on your sheet, just in case. Okay, so gas is freely moving, compressible. Pressure is primarily thermal, meaning as the temperature goes up, it's going to change the pressure. It doesn't have to do with depth or anything like that. That is what they're talking about there. It's constant in the laboratory-sized container. Loosely bound particles for liquid, incompressible. Pressure is primarily gravitational. That's why the deeper you go, we have gravity in here, the more we're going to feel it. And there's our hydrostatic. Okay, you do have one of these types of problems with Bernoulli's equation, and we have Bernoulli's equation down at the bottom, right down here. And you can rearrange that where you get P1 minus P2 all on one side, and that will always mean a pressure difference. And on your test, just FYI, it'll probably say, what is the pressure difference? Instead of saying what's the pressure at this point or that point, it's just going to want to know the difference of the two. You'll have to know the velocities of both gases. The height difference here is going to make a difference. So there is a Bernoulli equation, and here's our equation of continuity. That this is the one where you can figure out what the second velocity is. Okay, just going over for density. Okay, this is a pretty short, simple equation right here. So this would be more of a multiple choice type question if I asked you the density and given you two things, because I don't think that's worth a whole 10 points. So your multiple choice questions are pretty much, again, do you understand the concepts, and maybe just a few of the smaller little conversion type problems, you know, that you have to do for the bigger problems anyway.
That pressure one probably like right through.
Yeah, or maybe how much heat does it take to melt 2 kilograms of ice, you know, just little short things. Okay, we're showing the gauge pressure here. Pressure minus 1 atmosphere. Oh, 1 atmosphere for the, our total pressure minus the atmospheric pressure. You will have a buoyancy problem on the test. You can remember that you get the buoyant force by the weight of the water displaced. So if our object is at equilibrium, it's just floating there somewhere, the weight of the water displaced will be equal to the weight of that object. So perhaps like if they ask, well, what's the density of the object? Well, by figuring out the buoyant force, you could come up with the weight of the object, which then would give you could get the mass of the object. And from the mass of the object, you could also calculate the volume of the object, and then you could work towards the density. So that's the type of buoyant force problem you have. Did you follow all that?
Kind of. You find the buoyant force to be able to find the density.
Yeah, by finding the buoyant force, you can figure out the weight of the object. From the weight of the object, you can get the mass of the object. From the mass of the object, you can also calculate the volume, and density is mass over volume. All right, yeah, so that kind of tells you, I think that's kind of what the problem is I put on there.
I hope so. I hope it's not.
What is heat? We show heat with Q. Heat is actually the thermal energy moving from one place to another. Later on, we talk about heat flow rate, which then we take the heat, which is Q, and we divide by T. So this is just how much heat we have transferring, or how much thermal energy we have transferring, and then heat flow rate will be when we get into how fast is it moving, which it's not on this one yet. Okay, So Q is going to be positive if it is getting hotter, if it's bringing thermal energy in from around the surroundings. Q is going to be negative if it is moving heat to the surroundings. Okay, the evaporation part on here, we didn't talk about transferring heat. Might just throw it in there just a little bit. With evaporation, we are changing phase. We are going from a liquid to a gas. It takes heat to go from a liquid to a gas. So that will actually move the heat. That's why you get out of a swimming pool in the summertime and you're wet, you're cold, and as you dry off, you start heating up, but you're cold because that water on your body is trying to evaporate. I guess also sweat. Sweat on your body is trying to evaporate. To evaporate, it's going to take heat from your body to cause that phase change, and that's what cools you down. That's why sweating is going to cool you down. So that's why evaporation's on with this heat transfer also, but we didn't cover any of that in the class. Okay, so heat being transferred, this was showing by conduction. We have a hot area, we have a cold area. Heat always moves from hot to cold. This is actually what we would call the first law of thermodynamics, that it moves from an area of high temperature to an area of low temperature. We just didn't use that term in here. We have this material in between, so we will have heat moving through here, and how fast it moves depends on what this material is, the temperature difference, the area between that we have for the heat to flow through, and how long this is. So you will have a conduction problem on the test. Okay, I never called it the first law of thermodynamics, but here now when you hear about the first law, second law, and so forth, a little bit here, the first law just pretty much says that energy cannot be created or destroyed. It can move from one place to another, and this is what we use then for the calorimetry, where we will put something hot in cool water. We measure the temperature of the water that goes up, how much the other one goes down. We put Q equals to Q, and we can figure out specific heats. So I just told you wrong a little bit ago. The heat moving from hot to cold is the second law. First law is just pretty much the conservation of heat energy. For the people not here. All right, our melting point. We use an L in here for our heat transformation because it's latent heat, and latent means hidden. So the heat is still being added to the water, to the ice, or whatever, but we don't see it as a temperature change. We're just seeing it as a phase change. So it's like it's hidden in there even though it's still there. So our amount of heat that's needed to change the phase for fusion, which is the melting point, or vaporization, which is when we're going from the liquid to the gas, and it always takes more. This one over here is always higher. The type of problem that will be on your test might be something like we have ice at such a temperature and it melts and then it gets to a final temperature. How much total heat did it take to get there? I'm not doing all 3 steps, but you need to realize that when we have a phase change, that first of all, you have to raise the temperature, then you have to use another equation to change the phase, and then go back to the Q equals MC delta T to raise the temperature again. And ice and water and vapor have different specific heats. So that will be one of your types of problems that you have on the test also, the phase change. Okay, this means that the conduction, again, the D here is the delta. So the change in the heat over how much time depends on what the material is times the area divided by how thick the material is times the change in temperature. Radiation, do you remember what the E stands for?
Emissivity.
And you get that?
From the table.
From a table. What is sigma?
Constant.
Boltzmann.
1 point something,
Okay.
something.
And that constant will be given times how big the thing is, and
I thought that was area of contact.
well, this is like right now you are emitting, radiating to the room, so it's your surface area of your body. So it kind of is the area of contact. Your body's touching the air around it. So it's the surface area of the object, and then the thing is, the higher and higher the temperature, the more and more the radiation really takes off. Okay, there we go. On your test, it's going to start out with 10 multiple choice questions, which are on there just to see if you know the concepts. Some of the more simple math, like find the density, how much heat to change phase, little things like that. So it's the overall concepts, a lot of it that you see on the slideshow. Okay, let's see if I can remember all of these. You will have 7 problems. You will have to do only 5 of the 7.
If we do 7, do we get extra credit?
No, if you do them all, then you're like bougie and I'll give you credit for engineering. That's the difference between her test and yours this time, is she has to do more problems because her information was about the same. Okay, yeah, so you will pick, let's see, one of them will be something to do with pressure difference. For instance, you have a container with fluid in it, maybe 2 different fluids. The total pressure would be the atmospheric pressure plus atmospheric plus the pressure of this fluid, which depends on its density and its height, and this fluid's density and its height. So that's how you get your total pressure, and then there'll be some kind of question coming from that, like maybe what's the density of this fluid right here or something, which means if you figure out what the pressure is, you know, just work through there. But I think you have a homework problem somewhere, something like that. So pressure difference, there we go. You will have a buoyancy problem. Hey, this isn't too bad. Okay, let's see, with fluids, we had the Bernoulli problem, where we have something big and then it flows into something smaller. You get the pressure difference. Okay, let's see. From there, I think we go into, we had linear expansion. And we had the volume expansion. I can't remember which one I put on, but you're going to have some kind of expansion. That's 1, 2, 3, 4 so far. Okay. So that means my other 3 must be from the heat chapter.
You have the one equation.
You have the phase change thing. Phase change, which is like the heat curve. Okay, I promised you a conductivity. I think I promised you radiation. Is that 7? 1, 2, 3, 4, 5, 6, 7. That might be the type of problem. So those are the equations and things you want down. How do you feel about it?
I just don't like the pressure difference one. But I don't like those problems in general.
Okay, well, go back to your homework. I hope you can go back to your homework and redo it.
Yeah. Well,
Okay.
you can't redo it, but you can look at the solution guides.
All right.
If you pull down that, it walks you through it step by
If I
step.
do all my chemistry tests, it's like,
Okay. All right, well, that's great.
Tests don't have anything to do with this homework. If you noticed.
Okay. Yeah. Yes, the test is on Wednesday, and I'm going to try to get this on Canvas. I'll have to mess with it and see how it can get on there. That way, Lauren and poor JC, she'll only be here tomorrow and be gone again on Wednesday. So, yeah. So, all right. So that worked all right. I think I wrote better with my finger than with a stylus. All right, this isn't going to make any sense if I do it right here. They're not going to get it.